So it's secant junk, tangent junk. It's going to be a freaking disaster. Just wait. No, but I would only ask you for the derivative. I would not ask you to simplify. I would not ask you to go all the way to y prime by itself. Everyone understand that's just the derivative of secant junk. Now times, because chain rule says now you go inside, the derivative of what's inside. So watch this. We have a plus, don't we? We have a plus, so it's derivative of each one. Do the one on the right first. What's the derivative of y on the right by itself? No. On the purple circle there, the one on the right, what's the derivative of y by itself? Y prime. Okay, that's y prime, and stick it right over here at the edge. Plus, a little plus in front of it. Okay, but to the left of that plus sign, the purple, is a product rule. So what's the derivative of the product x times y cubed? 1 times y cubed plus, now very careful here. What is the derivative of y cubed? Times y prime. That is the big thing right here. And I'm even going to make a little side note here. If I'm trying to find dy dx, and I'm given y cubed, when I take the derivative, it's 3y squared. Most people are okay with that. Where does the y prime come from? That has to be out there. It's because, what if I said, what's the derivative of purple junk cubed? You would say 3 times purple junk squared, right? And then you would have to go inside and take the derivative of purple junk. But what's the derivative of purple junk here? The purple junk is y, isn't it? So what's the derivative of y? Y prime. It's not 1, though. Because it was x. So if you have, y is actually a function of x. Yeah, go ahead. Yep. Look, if we had this, watch, if we had x cubed, right? And I said take the derivative with respect to x. This derivative would be 3x squared, right? That's 3 junk squared times the derivative of junk. But in this case, I'm saying what's the derivative of x? X is my junk, right? The derivative of x with respect to x is 1. That's right. It's always been a 1, correct.
So would it need any other variable besides x?
Absolutely.
We're going to put the prime to it.
Yep. Okay, I'm not done? Times x. Okay, so that x, we kind of got off track a little here. That x was finishing off the product rule, right? So really, if I'm looking at it, this is kind of like my f prime g plus this big thing here was my g prime, and then here is my x or f, right? That was my little product rule going on right there. Are we done? No, that's just the derivative of the left side. So equals, I'm going to put the equals down here. So we have product rule there. So derivative of x squared is 2x. Now, yeah, there really is a 1 next step, but I'm not going to write it. 2x then. Hold on, slow down. Y to the 5th. Do your product rule. That's your f prime g. Right, f prime g plus, now careful here, derivative of y to the 5th. 5y to the 4th times y prime. And then times x squared. Now, theoretically, you could get y prime by itself here, but like I said, I would not ask you that. On the test, I would say find the derivative only, do not solve for y prime. But do you see how this one problem incorporates a lot of what we've learned? We've got chain rule, product rule, we've got implicit differentiation, the idea of junk and derivative of that. I mean, it's all in here. It's a good problem. You want another one? Pardon me? Yeah, that's, you would just box all that if that's all I want. So let me give you one to see where you are on this, okay? Why don't you try this one? You can work together if you'd like. Just a little exercise here. Tangent cubed of xy over x plus y plus x squared y equals 1. I want you here to find dy dx. And I'll give you about, I don't know, 5-10 minutes. I'm going to pause the video while this. All right, so the first thing you have to see is that this right here, the yellow is my junk, and that's yellow cubed, right? The derivative of yellow cubed is what? 3 times yellow squared. So 3 times yellow, but yellow is everything there. Now how do I say squared? I can either put the whole thing in parentheses like this and square it, or I can just put the 2 on top of the tangent. Either way. That's the cleaner way, just like this. Okay, so that's 3 tangent squared of all that junk. Now, times. I have taken care of the 3. The next thing I have to look at is I've got tangent of some junk. The blue is my junk now. What's the derivative of tangent of blue? Secant squared of blue. But blue is xy over x plus y. Questions on that? Next thing, I'm done with my tangent. So the next thing inside is a quotient rule, isn't it? I have an f on top and a g on bottom. So what's the derivative of f over g? It's f prime g minus g prime f all over g squared, correct? That's what I would have there. That's what I need. That's what I need to put here. Now the g, I'm going to kind of do the easy parts first. Well, no, I won't do the easy parts. I'll do the hard part first. The hardest part is the f prime, right? Because look at your f. Your f is that xy on top. What's the derivative of xy? Well, that's a product rule, right? So derivative of x times y turns out to be what? 1 times y plus y prime x. That's just f prime. Then next to that you need what? X plus y, that's your g, minus now g prime. Now g, which is the denominator, is a sum. So you take derivative of each one. Derivative of x is 1 plus y prime, and then f, which is xy, then all over g squared. I'm done with that big tangent cube thing now. Then I put plus, and now I'm just going to do the derivative of x squared y, which is another product rule, right? 2xy plus y prime x squared. Then equals what? 0. That would be acceptable on a test. Okay, I want to show you a little bit more here. What time do we take our break? 2:45? Is it 2? Yeah, it is, right? Isn't it 2:45 we take a break? No. It's 2:45. Shit, man, it's a long day. All right, look at this next example. I want to really make sure you understand what's going on here. X squared y cubed equals x plus 3y. Find dy dx. Now, this problem is not supposed to be hard. I just want to make sure we're on the same page. So what do we have happening on the left? Product rule. On the right side, it's a sum, right? So I can just do them each one. Okay, so what's derivative of the left? Careful. Y prime x squared. So again, it's that y prime that you got to be careful about, right? Equals what? 1 plus 3 y prime. What's the derivative of y with respect to x? Y prime. It's dy dx, isn't it? Any questions on that? You could treat it like a product, but it's way more work than you would have to do because it's a constant in front of a function. So all you do is ignore the constant and take derivative of the function. All right, now the reason I'm doing that one is because I'd like to illustrate that, compare it to this one. X squared y cubed equals x plus 3y, exact same equation, right? But I want you to find dx dy. What the hell does dx dy mean? That means you're going to treat which variable like the independent variable. Y's this time, anytime I take the derivative of y, it's 1. And anytime I take the derivative of x, it's x prime. See, it's backwards from what we've just done. So let's see if you can get this now. What's the derivative of x? Well, this is a product rule, right, on the left. What's the derivative of x squared with respect to y? 2x x prime times y cubed plus 3y squared x squared. Good. See, this time the y prime's really a 1. Equals x prime plus 3. I told y'all about that girl, right, that I went out and danced with that night, the engineer, right? I told you about that question I asked her about reaching into the interval 0, 1 and probability of picking out a rational number. Well, I kind of lied to you. The first question I asked her was, what's the derivative of x? And the answer I expected to hear from her was 1. But her answer was, with respect to what variable? And I was like, ooh, that's pretty impressive. Because it matters, right? If I ask you what's the derivative of x with respect to y, it's x prime. It's dx dy. But if I say what's the derivative of x with respect to x, it's 1. So that makes a huge difference, right? And that's what implicit differentiation is starting to get us to kind of look at. Your variables now, what you differentiate with respect to, will determine what the derivative looks like. Now, what is the difference between these two things? Like geometrically or physically, what's the difference? I'm asking this, but I'm going to answer the question. The first one up there is basically telling you the instantaneous